Hi, welcome to Multivariable Calculus, Lecture 18. It's an exciting day. We're going to start vector fields, which is sort of the last big topic that we're going to cover. This whole thing gets a funny name of vector calculus, which you might say, what, haven't we been doing that the whole time? Short answer is yes, but that name gets attached usually to these big theorems about the change of vector fields, right, their differential properties, and what happens when you integrate them. As a way to get into it, let's do a real fast review, basically, of the entire course. So imagine a bee flying around this room, or the room you're in. Picture it in your minds. If you don't literally have a bee flying around the room, how do you model that? Well, since position is changing in time, we use a vector valued function. So the input is a scalar t time, output is position vector, right? Those are the first things we studied. They're also called curves to reflect the path of the bee. All right, now let's add some structure. Suppose the temperature is varying in the room, right? I'm warmer, the cool by the air is coming in the window, the radiator is hot, right? Varying temperature in the room. How do we describe that? Well, temperature is a scalar, right? One number of degrees will do it, but it could be different at different positions. So there we need a function where the input is vector position, say, and the output is a scalar. Those are functions of several variables, also known as scalar fields, right, that we've been studying recently. And we did something neat. We married them together, right? We said, okay, what if the bee wants to go toward the warm parts? So the bee, right, feels some temperature nearby and says, I'm going to go where it's warmer, right? That's the place for me. Mathematically, we describe that in a really kind of elegant way. We just say, okay, well, wherever the bee's headed, that's the derivative, right? That's a vector. Line that up with, right, the direction where the temperature is changing the greatest. That's the gradient, right? Vector. And so the gradient says go this way for warmer temperatures, and the bee says fine. Its derivative, right, the derivative of its position, of its velocity, right, heads in that direction. Right. So it's a cool story so far, but what if we want to add some more structure? I open the window, right, or I turn on the air conditioning and there's wind. Right? How do we model wind? Well, wind is, right, it has direction and it has magnitude. Right, it can blow stronger and it can go northwest, east. Right, in the room it can point in any direction. We need a vector to model wind, and it might be different at every different position in the room. That's what a vector field does. All right. So that's what we're going to do today. We're going to look at vector fields, a couple of examples real fast. We'll dive into a lot more in the class meeting. And then I do want to define conservative vector fields so that you know what that word means and you know them when you see them. And certainly it's important to recognize not every vector field is conservative. Here. So jump into the definition. A vector field's a function, right? Everything we study so far is a function. It's just now the input, right, is multivariate. So we say Rn, right, for tuple of n scalar inputs, and the output, right, is also a vector, right? Well, for now, let's take n and n, right? The input and the output are the same dimension, although we'll relax that in some things we'll look at a bit later. So starting in the plane, right, is a good place to start. So we have a vector field in the plane. The input or positions in the plane. So we have the two components, x and y, right, are the inputs. Notation-wise, we usually use that bold. Notice the bold F here. And that's good. The reader knows the output is a vector, right, there. And so what do you need for a vector? Well, you just need a scalar for each component. So for each input, we have one scalar for the horizontal component, and we'll call that P typically. Right, here's a capital P. So capital P itself is a scalar valued function, one of the old things we studied. Right, so it just is the one component of our vector field. And then Q could be the vertical component, right? And in 3 dimensions, R, and so on. And you can tack on more for higher dimensional stuff. But this will be a typical setup to begin our study of vector fields. You really just have 2 functions in the plane, one for the horizontal component, one for the vertical component. So algebraically, these things are not very sophisticated. This is a really important example, but it looks really boring as in its formula, right? Minus y, okay, that's the first component, right? X, the second component. I probably shouldn't be using I and j in the plane, but I think you know what I mean. This will represent 1, 0, and j will represent 0, 1 here. It's not a 3-dimensional vector field. So this is an important vector field, and how do we know that it's right? That it's important. Formula-wise, it looks pretty boring. But when we look at it, by which I mean we're going to try and plot it to have some visualization of this thing, it looks a lot more interesting. So a vector plot is our attempt at a graph. Obviously, we don't nearly have enough dimensions to do a proper graph where, right, every value of your function is represented here. But instead, since we're in the plane, at each value of the input, right, the output is a vector, we can mark that by just drawing a little arrow at each input. And we can't do it at all the inputs, infinite number, that would be a jumbled mess. And as we'll see, we can't really literally plot the vectors in most cases. But what we can do is select a bunch of points, enough that the reader can understand, get a nice representation of the values of this function. And then at each point, plot the vector associated with the vector field, right? And with a little bit of scaling, right? So here's a little bit of the code got included here. You see that Python's a little clever. It uses quiver for vector fields, right? Meaning quiver, meaning a bunch of arrows, right? Haha. There, but you can see it's being plotted here. So the input is x and y, and you see the output is minus y, x there. And this is the picture that this guy produces. And of course, it picks a selection of points at which to draw the arrows, or I guess I picked 20 points across here. There. At each one, it draws a vector, but it doesn't literally draw the vector, right? Look, for example, at 2, 2, right? The actual output vector 2, 2, right? If I drew the whole thing, it would be like that, right? That big, and that's clearly, right? Clearly silly. So we scale them all down, right? So that the reader can view them. Right? Vector plots are for humans, right? To understand the vector field. Computers have little use for these pictures here. But so at each point we plot it, and the relative size does matter, right? Notice for values close to 0, right? X and Y close to 0, small values. The arrows are smaller, the components are smaller there. As we move away, this thing gets bigger. So the way to understand this vector field is, right, it's as this field of arrows. But if you're like me, you can't help but doing something that's actually pretty sophisticated, which is called integrating this vector field, which really just means following the arrows, right? So when I describe this vector field, I call it a circular vector field, right? Not because any of the functions are functions of circles here, but if you were to kind of follow these arrows around, meaning, and we can make that rigorous, find a curve whose tangent vectors are equal to this vector field at each point, right, of its output, we would see circles, right? This vector field represents tangent vectors of circular curves here. And our brains are really good at this, right? And finding the formulas is another matter entirely, in fact, for another course. But for just visually integrating vector fields, you can do that right now. You can teach your 5-year-old cousin to do this as well, right? By just following the arrows and draw a curve where they are. It's a good way of describing the vector fields and just getting a feel for their behavior overall. Okay, so this is a good example. We're going to use this, right? Simple seeming vector field. It's going to come up a couple times as we go. Here's a radial vector field by contrast. So notice now the components are just x and y, right, in a different order. So the functions are just as simple, right? But now x is in the horizontal component, y is in the vertical component. Notice this is sort of like the identity function, right? X and y come in, and x and y come out in that order. If we interpret the input as a vector, right, the output's the same vector there. So in that sense, it's the identity here. But if we plot it in the same way, it's called the radial vector field because it points outward, right? It's kind of like running away from the origin, right, as to how it looks. And the farther it gets away, the kind of faster it's running. Right? So I'm kind of visualizing these arrows as being sort of velocity of something moving away from the origin. And the descriptive terms like that are good, I think, in understanding vector fields, right? Trading formula is not so good, but radial vector field is nice in descriptions. Radial because it's kind of symmetric in all directions. Okay. Notice it's got an interesting relationship to the last one. Here are the last two vector fields plotted right there. And if you notice, right, oh, they're actually, right, that little angle there looks like they form right angles. And you're allowed to compute with vector fields is the point here. Right? It's perfectly fine to do that. The outputs are vectors, so we can do vector operations. So I can take something like f that I defined earlier, right? I'll put an arrow on it to say that it's a vector field, dotted with g here. And so f's a vector field, vector at every point. G is a vector field, vector at every point. I can dot the outputs of those two guys. I'm going to get a scalar here. Which scalar am I going to get when I dot these guys? Right. Well, remember I had minus y was the first component of f times x plus xy. X was the second component of f, y is the second component of g here, and lo and behold, of course, we get 0. So we can use our analysis and our vector operations we've had to analyze vector fields. This way we can compute with them. That's what I'm saying here. All right, let's I forgot what the clear button is for this little setup. I'll move on. So 3D vector fields, formulaically, they're no more complicated. We have an extra component there, so I, j, and k really are legitimate. Here, sometimes some of the components don't appear. So, right, this example f here is just x times I, but that's still a vector at every position, right? You look at the position 1, 1, 1, its output would just be I, right? And the position 1, 3, 3, also the output is just I for this guy. But notice it is a three-dimensional vector field. We just assume it's 0 for the j and k components there. And then even just simple mixing up of our functions, the problem with 3D vector fields is they get a little ugly, right? Here's that picture of just xi. And here are some of the other pictures. You can play around with these with the slides. Great for computers. Don't graph these by hand. You're going to drive yourself nuts doing it. So there are a number of important physical examples of vector fields, right? Wind was one that we already saw, but sort of two big ones to think about are examples of vectors that we've seen. One is the one I was mentioning of velocity here. So like wind would be a good example of that. But it's good to think about flows, just flows in general. Fluids in particular, right? Fluid dynamics is a huge and important study. A lot of our climate modeling is really just, not just, but a huge part of it is fluid dynamics, right? The atmosphere is a fluid, right? It has, right? It moves around a lot, and in intricate and complicated ways in 3 dimensions, and it's a very, very complex system. But in a lot of ways, chief way to understand it is through like flowing of a fluid. Air is here; it's at a certain pressure and temperature, and water content, and it moves somewhere else, right? We'll go according to certain laws. Anyway, so we should understand, one way to understand a vector field is as flows of particles, right? Of some fluid here. And so this picture was made for. This is for a very particular kind of vector field here. But notice it's just all these little dots here are supposed to represent particles, and they're doing that thing of following the arrows, right? Notice where the arrows are longer, which is over here, they move a lot faster, right? They seem to be condensing over here, but they're moving away out here, right? You kind of watch them go. So it's a good way to understand, right, a vector field. And then, right, a lot of the equations and fluid dynamics are differential equations. They have a time component, right, often to them, and then the dependence of the flow will depend on all sorts of things, the depth of the water and the compressibility of your fluid, the pressure, right? All those come into it, into those models there. But for your perspective, right, is just to think about, okay, right, a vector field can represent the velocity of a fluid, right, meaning at each point where the particles are moving here. All right. Another important example is gravity. I think I might reserve this slide for later. But gravity, when you first study it in like kind of just an algebra-based physics class, they just talk about two massive bodies attracted to each other, right? They're always attracted to each other. And it's GMM over R squared, right? So it's the farther apart they are, the less, right, the attractive force is. When they get closer, they get more attractive there. The more sophisticated way of looking at it is now as a vector field, right? That one massive body induces a gravitational field, right? That's what this guy says. We'll look at the details. I do want to kind of dive into some of these, the formulas, the subtleties of why is that square root there, and what is the R squared doing here? But big G is a constant, right? Big M is a mass. R is the distance between masses. So in this case, we've got a mass at the origin, right? R is literally x squared plus y squared plus z squared, which I guess we could call it rho in our spherical coordinates there. But it's the distance, right? Distance squared here. So this field gets weaker as you move away from the mass. Right? Here's a picture, right, of two masses. The neat thing about this framing of gravity is that if you have two bodies, right, and you want to know what the field looks like, and you want to know what the combined gravitational field is, you just add them, right, which is great, right? Vectors can add. We can use our vector operations, and so you have your two vector fields. You can add vector fields, and so it's very nicely. So you get two masses. Each one has a vector field pointing toward it, right, so that another mass will be attracted to it. But overall, what's the effect? You literally just add them, and you can get a feel for what the sort of sophisticated system looks like. There is sort of a equilibrium zone here, right, where the forces from the two bodies are balanced out, right? You can kind of hang out in between them, even if they're not the same mass. Somewhere in between them, right, closer to the smaller one, will be a zone where it's actually perfectly balanced, and just a little bit on either side of them kind of will determine your fate of whether you're going to end up getting pulled into the bigger one, or you're close enough to the smaller one that you'll get pulled into there. Right. The only thing I want you to take away from this picture is that a vector field framing of gravity is useful, because then more bodies into your system, you just add the fields, right? The power of vector addition is there here. And there's a great bit about electric charge. Another fundamental force, right, is the electric force, electromagnetic force in physics. So matter, right, can have mass. It can also have charge, right? So we use Q for that. And when you go and look at how particles with different charge are attracted or repelled from each other, if they have the same charge, they're repelled. If they have opposite charges, it turns out they're attracted. So mathematically, the only difference here, right, is the sign. Right? Here's an electric field induced by a particle with charge big Q. Right? So big Q can have a sign. Right? Mass is just positive, but big Q can have a sign here. There's no negative sign here. Right? So ignore these constants, right? Permittivity, yada yada, 4 pi, and so on. Right? What the important bit is, a particle has charge, right? The distance squared still appears, right, in the denominator here, right? That means small distance, big attraction, right? Particles very close to each other pull very hard on each other. When they're far away, they barely feel the effects. As well, distance over r squared, same as as in gravity. The only difference is the sign here is positive, but that reflects that idea, right, that like charges are repelled, right? So another positive charge is going to have a vector, the electric field is going to run away, right? Its force is going to be away from the charge. Here the charge is at the origin. Whereas a negative charge, right, you'll multiply the electric field by the negative charge, you'll get force toward the particle. There. And so the story I like to tell about this framing of these two things, right? Gravity here and electric force here. When I entered undergraduate school, I had an overinflated view of my own physics understanding, naturally. But even then, I knew that, I was like, I understand mass, but charge, I knew I didn't quite have a handle on, right? I felt like, gravity, cool, I understand, I got that down, right? But charge, electric fields, I didn't feel like I had a grasp on what that really was. And then I saw this framing of it as fields, and that they basically are the same form, just, mass always positive, attracted to each other, right? Charge can have any sign, and the opposites are attracted in that case. And so I finally realized that instead of knowing mass, understanding mass, and not understanding charge, that in fact I understood neither of them at all, and that was a bit relieving. I felt better about myself. Okay, last bit, right? Actually important rather than stories of silly thoughts of a first year long ago. Are conservative vector fields. So this is a definition of a certain kind of vector field, and there are vector fields we've actually encountered. So a vector field is conservative, right? Has nothing to do with a subscription to the National Review. It has to do with it having a particular form. In particular, it is the gradient of some scalar field. All right, so that's important. A vector field is conservative if there's a scalar field, and we call that a potential, right? And so our vector field is the gradient of that. This would probably be easier if we just called them gradient fields, right? So you've got vector fields, and some of them are conservative, right? It means they're the gradient of some function, but not all of them, right? If you write down a vector field at random, actually, you just pick a function for the first component, and you pick another random function for the second component, chances are it won't be conservative, as we'll see. But some are, and we've encountered gradients before. They are vector fields. They are conservative vector fields. Right? So lock that definition away. When you hear the word conservative, think gradient. Right? Just put those two together in the context of this class. Right? Right? It can mean other things. In other classes, we'll see where the word comes from. Right? What gets conserved by conservative vector fields. That's coming soon. So a couple of real quick examples. The radial vector field, the one that runs away from the origin, that thing's conservative. Right? It's easy enough to see. Here's its potential, x squared plus y squared over 2. Right? So how do we see that? We'll take the gradient. Now this scalar value field, right there, this is the potential function. Right? So when you take the x derivative, what you get is just 2x over 2, which is x. When you take the y derivative, you get 2y over 2, which is y. It's conservative. Just it fits the definition. Right? Here's the function whose gradient is this guy. If you want to prove that a function is conservative, right, produce the potential, right? I said the potential, but it's really a potential. I can add any scalar to this, and it's still a perfectly fine potential for it, right? Any scalar I add, a constant will cancel out, so it's also the gradient of that. Okay, so that's a thing, and as a last thing, well, what about our circular vector field? Right? What's its potential? Right? Is it conservative? Right? And don't be surprised. Right? The way to frame that question is, okay, can we find a scalar field f where the x derivative is minus y and the y derivative is x? Right? Can we do that? Could it be as simple as this? And the answer is no. No such function exists. You can try all day long, right? Trying out different scalar valued functions, take an x derivative minus y derivative x. It'll never happen there. And rather than just trying it all day and having a conclusion there, right? The funny thing is, to check this, we actually take derivatives. and not integrals. We don't find antiderivatives integrals. So this is Clarins theorem again, right, which says that if we knew if there were such a function f, where fx was minus y, well then fxy would be minus 1, right? Because I just take a y derivative of fx and I'd get minus 1. But the same function has a y derivative of x, so fyx would be 1. Those are not the same thing. Right? So what's the conclusion? There's no function, there can't be no differentiable function anywhere out there whose y derivative is x and whose x derivative is minus y. It just doesn't, simply doesn't exist here. So those signs really mattered. It's not conservative. Okay, right, so not every vector field is conservative. This little trick is a good one to employ often, right? You encounter a vector field and you might ask, is it conservative, right? This question, this Clarins trick, by checking mixed partials, you can certainly determine that it's not conservative this way. Now, of course, you might say, okay, well, what if they do match? Does that mean it is conservative? And that's for another day, right? Often, not always, right? There, it's trickier, but we'll get to that in other examples. All right, that's a fast introduction to vector fields. We'll work a whole bunch of problems. Maybe we'll talk a little more directly about like gravity and electricity to get those down, and then we're going to dive into line integrals, which are a new kind of integral, which will join up with these guys soon enough. All right, I will see you in class.